we are going to launch Xilinx Platform Studio. There are various tools in Xilinx, like Xilinx Software Development Kit and Project Navigator. So if I type Project Navigator, okay. So the first step to test any IP is to do a project in ISV. So what we are going to do, we are going to interface an IP in EDK. So before doing that, we will create a project in ISC and test whether it's working fine or not. So I'll go and make a new project. So the name of the project is adder1. Adder1. So it says that the C user desktop adder is not a location for your project. Make some other location. So I'll change the directory because C directory is the path for installation of Xilinx tools. So that's why it is saying to take a different. Okay. So in the E drive, I'm changing the path. It's now adder1. Now the kit which we are going to use is ML507. The FPGA available on it is XC5VX FX70T Vertex 5 series FF1136-3. So I'll put the grade speed as -1 and say next. So it will show me the summary, right? Then I'll say click on project, add source. I'll add the simple adder, and this window can take us to different IPs available. So right now we are interested in VHDL module. Name of the module, let's say, is adder. Name of the project was adder1. So this file will be created. Now what I'll do, my adder file is already created. So my adder file is already created. So let me show you the adder file. This is a simple adder file written in VHDL. So there is a clock input, A input, B input, sum is the output, and behavioral model has been used to describe the addition process. So I will take this, copy it, and paste it on this one. Okay. So the next step is to check whether the syntax is correct for the code or not. This is a standalone IP for an adder application. I'll go to synthesis and check syntax. Synthesis takes a little bit time because the design is very small. That's why it is finishing in very less time. It will show a green circle here which says that the syntax is correct. After that we can click on synthesize the design on the FPGA which we have selected. Now a couple of steps will be shown in the window, and during this process you can see the mapping of different onto the different LUT and FPGA resources, and then design summary report will be generated which will show you the amount of slices present, available resources. You can see the available resources are 44,800, and the adder has used 32 slice LUTs, and there are other resources as well that can be seen, number of bounded IOs and global buffers and so on, right? Along with this we can see the RTL schematic. So this is the RTL schematic. Just click on it, right click, and show block contents. It has directly taken an adder block onto the IO, so it's not showing the low level modules. Show that will be input and outputs only. So our input output is already available. No, so it will only show adder. It is not going to show because this is not a gate level design. In case of a gate level design, it will show the component, but here it's an LUT based implementation, so it will only show an adder here, right? So this, with the help of this, we can see the generated file. Right. So we are not going to implement this onto the real FPGA from this project. If we want to test it on the FPGA, we can do it. Then here we have to add a UCF file. Right now we are not adding the UCF file. So if you want to test the functionality, click on simulation, click on adder, click on simulation model sim simulator, click on simulate Bevel model, say yes. No, okay, model sim is launching, iSim is not launching. Yeah, yeah. Here we can push the different values and see the output. Okay, so first of all the clock, force the clock. Let's say the clock is 1 0 and period is 100. Apply. Okay, the next one is 32-bit value. Let's change the radix of this to hexadecimal, and now change the value to force constant to a value of 23. Apply. Okay, change the radix again to hexadecimal, force it 59. Apply. Okay, sum also the radix has to be same. Now we can click on run all. So the result we are getting as AC. That is how we can do the simulation of standalone IP by pushing the input signals along with the clock should be correct, and it's continuously running. We'll stop it now. It's 100 when you put 100, it's 100 picos. 100 picos, yeah. So for every cycle it will that much run. So now we have completed the testing of the IP adder. We next move on to the Xilinx EDK platform and launch the Xilinx platform studio. Create a new project similar to the one we have done it right now. So here it will ask you two kind of bus systems, PLB based or EXI based. We are working with the Power PC processor on ML507, so we are choosing PLB bus. This GUI will turn up asking for board, system, processor, peripherals, and cache configuration. So step by step, we'll now do these steps. The first one is to select the ML507 board. This is important because all the on-chip peripherals will be automatically selected if we select the right board, and it becomes much easier for us. So now I've selected Vertex 5 ML507. There is no particular reason to select it. This board also supports partial reconfiguration. That's the importance. So in the next step, it will ask whether it's a single process system or a dual process system. Right now, we are only making a single process system. It is also possible to have more than two processors in the system. So the selected processor is PowerPC, and the frequency which is selected is 125 MHz is the default frequency. Although PowerPC can run at 400 MHz, but 125. Right now, we'll stick to 125. Floating point unit will not click on. Okay, so these are the available peripherals on the board because we selected the board. We can remove or add these peripherals. First of all, DDR is there. I'll remove it. I will try to make a minimum project with components so that the project compiles in less time. LED removing PCI bridge. The more the components are chosen for implementation, bigger will be the size required of the bit file. and larger area will be utilized for the FPGA. So compact file also remove. I'll just add a XPS timer. This timer we usually use to for timing purposes. So with the help of this timer we can measure the timing. So these are the minimum components that are chosen for. So next step it is asking the amount of cache memory from which component. So we are having instruction cache of SRAM which is of 32 KB for PowerPC and data cache of 32 KB for same from SRAM. So finally it will show the peripherals which will be generated for example applications. So once we move to the software development kit, we will see all these uh, tests being generated by the code. So we chose these components GPIOs, UART, DRAM timer. So the system automatically generates the base addresses and the last address for each of these components. That's the advantage of using these tools. Otherwise we have to manually perform this operation. Okay, you must have done this in. So along with this, you can see many other files are automatically generated like XMP file, MHS file, MSS file, UCF file. These were meant for processor specifications and IO specifications are written in these files. So we will open and see these files as well. So once the system is created, we have a system assembly view and a block diagram. If we click on block diagram, so right now we have a power PC, we have a system reset, we have a JTAG along with which we program the memory. We have these components which are on the board. We have a clock here, clock generator, and on this side we have the block uh, DRAM controller, right? So these can be easily seen in the block diagram view. Along on this panel we can see the IP catalog. In the IP catalog many IP cores are provided by this tool, and this repository can help us to have different components. So let's see, if I want to add a component partial reconfiguration, I'll click on double click on it. It will say do you want to add the instance of this design to your current design. I'll say yes. So it will ask the parameters for configuring this IP. In this case it is write FIFO depth, read FIFO depth. I'll say right now click OK and take the default configurations. So we'll see that this component has been added. This component has been added, but we'll see there is no connection over there. So again, if I look in the block diagram window, I'll find there is a component which is not connected to anywhere, but it's still there. So in order to do the connections, we have to manually connect it to PLB, right? So that is the process of interfacing an IP, and then I have to click on generate addresses because this IP is not interfaced to any of the, not mapped to any of the addresses. Click on generate addresses. Right, that's the conventional process of adding an IP. So right now what I'll do, I'll remove this, read the instance. Uh, Step in this process is to create a peripheral and import a peripheral, right? So exactly what is done in this process is, first of all we create a black box. So let's assume we want to create a black box. So the black box is named as a user logic file. So the first condition here is to create a box like this, and name for this is given, let's say ADDX. Okay, internal to this one is one more block which is known as the, this block is known as the user logic, and inside the user logic we have one more block which we are going to add is our adder. So there are three levels of hierarchy. So the adds X has the interfaces for PLB bus. So on one side it communicates with the as a master, and on one side it behaves as a slave, right? Inside the user logic we have connections coming from this add X to user logic, and my component adder is within the user logic. So first of all what we have to do, we have to instantiate the adder inside user logic and then interface it. So that's the next step. So we go to the project, no, hardware, create or import peripheral. The first we have to click on the first choice, create template. So I'm creating the black box right now, name as add as, that's the top level box. So it will ask you two kind of links which are available for interfacing. First one is the processor local bus and the other one is the fast simplex link. Fast simplex link is a point to point connection between the processor and the IP. So it's a faster link for working at a higher speed. But PLB bus is a conventional bus which can be used to interface an IP. So we are going to try with the PLB bus. So the next step I told you is to this template will be created black box in which there will be a PLB slave interface and there will be a PLB master interface. There will be a user logic file and within that we will be writing our code. Along with this there are 6 options which are shown here. The first one is software reset. If you click this one, there will be a software reset which you can use in your software programming. Once you insert the software, your entire system will be reset. Or else you can use read write FIFOs. That means these are the channels, first in first out channels for your IP. Based on what kind of techniques you are using for your IP, you can use either FIFOs or you can use slave registers. So we can use FIFOs or we can use software registers or we can use memory space. That means depending upon what kind of IP you are creating, any of the three are possible. So here in this next step it will ask whether it is looking for a bus transfer or on the cache line. So we are not going to select this one. So because we have selected the slave registers as our interfaces to the ports, it will ask how many registers do you want. The maximum possible registers here are 4096. So let's say we have A, B and some. So in my case I am using 3 registers to put my design to interface. Right? So next it will ask the bus signals. Just click on this part. I am not generating a simulation model for bus for model sim. Don't check it right now. Now in this step it will say whether your user logic has to be in Verilog. If it is in Verilog you have to click it, right? But then lot of changes are to be made in the file. It's better to write the VHDL instead of Verilog because this requires lot of editing. Better to not to check this step and write the file in VHDL. Next 2 lines are for generating ISC projects and for creating a template for drivers of the software interface so that we can program the. It is also possible we click none of them, then also the project can work with certain functions. But then with this, a driver folder will be created which will be useful. So now we have finished creating a template which is a black box for our design. So once we go to the this project directory, so we will see a folder created name as P course, which stands for peripherals course. So inside that we will see whatever name was given ads will be created here. Inside this we will see lot of other directories. First one is the data directory and there is a file which is known as PO file, POW file, and this has the description of all the components which are there. So if you go by step, if you call, we had these 2 lines are referring to other user logic file and the upper level file, and the other components are there for the processor, adder, decoder, attachment. So these are respective to the bus signals. Certain changes are to be made in this file as well. So the next directory here is development, which is respective of the design. HDL has 2 files which we have shown in the PPT, user logic and address. So the first black box and the inner one, these two. We have to edit user logic file and add. We have to edit user logic file to put our adder. So the first step that we are supposed to do is to copy the adder file over in this directory. So we will take the adder. Now after doing this, we are supposed to add the line in the POW file so that the system knows that this has been added. We'll open the POW file here and add few lines. So we add the third last step. We are supposed to add this line. Look at, we have to go according to the hierarchy of the files. The upper level file is addx, then user logic, and then adder. It's the We cannot paste it at the bottom because the hierarchy will change. Remember, the hierarchy is given in this slide, which is adds, user logic, and then adder. Okay, this file and exit. We can close it here. The next thing we have to do is to add the instantiate the adder, right? So we'll now open the uh, user logic file and make changes accordingly. So if we go to if we keep reading this file according to the lines given, it becomes very easy. It's written as add user ports below this line. So this is the condition at which we are supposed to add the ports. So after this line, architecture IMP of user logic is we are supposed to instantiate the adder. So the first step is to instantiate the component. So the component is adder here, and it's already pasted in the directory. So this file will understand, and the pow file tells that this adder is available in this directory with the hierarchy. Okay, so that's the first step. So the same port, remember the same port definition should be there as it's in the adder file. Otherwise, it will give an error, right? After that, after we have instantiated the components, the next step is to map the signals of the adder, clock, AP, and sum to the slave registers. We have selected three slave registers. So A is mapped to slave register 0, B is mapped to slave register 1, and sum is mapped to slave register 2. We can also see that slave register signals are added on this line. This was done during the previous step because we gave default as 3 registers. As many registers will give, so many will be instantiated here automatically, right? So that's the next step. Thing which we are going is to add the output, which is sum here, as a signal. Now this sum has to be declared as a signal because it will be interfaced to the output port and should be declared as sum. We will save this. This is the third change. This is highlighted here, and we have whichever is the output, we have to comment out that particular statement. So we need to find which are the output ports. In our case it is uh, slave register 2. So the slave register 2 is written over here because this is an output, right? So that's why we have to comment it. This is a state machine which finds out which is the register on which we have to get the output. A state machine is starts at the starting at the cases here, and accordingly it is selected. So we will comment out these lines. Based on one more thing which is to be commented, which is slave register 0. As I said that any output signal which is mapped to these registers should not be in the state machine. This is a state machine which follows the register inputs. So I have commented one more line is highlighted here. I think this completes the editing of user logic. So the next step is to import the file we have created. We have just created the black box. The next step is to import. We'll go to the same thing, create import peripheral, and instead of creating template, we'll import the peripheral now. Say next. Yeah. So this is going to be a XPS project. Same. We will give the same name here. Add as. Yeah. So next thing is now in this file, in this we are supposed to specify the POW file. We have made changes to the POW file. So here we have to give the path of the POW file because in this file the hierarchy is there. If the hierarchy is correct, it will be visible here. If the hierarchy is wrong in your file, adder, then user logic, then add this. Otherwise, this will be shuffled and it will say error. It looks for this order. So you have to paste correctly in the POW file, right? Okay, so we see that the hierarchy is correct here. Next, it will ask that what kind of interface it is. It was a PLB and my IP is a slave interface. It's not a master. So I'll click on slave. Okay. Now on this step you can see all the signals here are signals on one side on the PLB connection and my port. That means these signals are present in addS, the upper level box, and these signals are there in the PLB connections. So if they are correct, they will be automatically mapped. That is the step. There are many such signals which will be automatically mapped. There are certain cases in which if you have not put it properly, this will give an error. Because in this case it's fine, it will go register space, the base address and the higher IO address is already given. And then we are not into the stuff of interrupts right now, so I'm removing the interrupts. This is done. Now we will see on this part there is add is available. I click on it. Now there will be an instance which is added to the IP. So just leave the default condition, make a connection to the bus. Right now it will not be connected, will be connected, and then go to the no addresses. Click on this, generate addresses. Addresses will be generated, and it will see that to compile the project, which should take around 20 minutes. So the next step is to export hardware design to SDK. Now we have created the hardware platform. The next step is to create the software platform, and click on launch, export and launch SDK. So at the bottom window, it will around run for 20 minutes. If there is any error in the user logic file, it will show here. And it's better to read the warnings also, because in certain warnings also there may be errors involved in the design itself. So keep going through the step by step, which is going in the background of the processes. So the next step here is to if the design was successfully interfaced, that means the adder was successfully interfaced, and it showed no error, this window will pop up. This window is an Eclipse environment, and you can see here three files will be exported. One is the BMM file, bit file, and XML file. BMM file has the binary memory map. It's a kind of file which has information about the BRAM controller. There is a bit file which is implemented on the system, and the XML file which has information about each IP and its addresses. The next step here is to generate the one layer of software. The first layer of software is the board support package. So we'll go to new and generate a board support package. Okay, board board support package will create a library here, and the SDK environment, which is an Eclipse environment, has a cross compiler for PowerPC and Microplace. So that's the only difference thing available here. This toolchain is able to compile any C program for PowerPC and Microplace. So let's click on next. So on the left side, we will see a folder is created. In this folder, various other files are also there. In this step, it is asking whether you are looking for any file system. So if you are working with CF card or flash memory, you may look for different file formattings. Right now we are only working with SRAM, so we will not click on any of them. But in case you are working with CF card, you may have to click this. So at the bottom we will say these files are getting generated, and the cross compiler, you can see PowerPC EABIAR is the cross compiler which is generating the library for the C program. So once it is done, it will show the library being created on the folder under standalone BSP0. It's to create a C application. So let's try creating a new Xilinx C project, and let us first only test the hello world program, and I'll click on next. So again on the left we will see that again board support package has been implemented as standalone BSP, so we'll select this one, finish. So on the left we will see a hello world application has been developed, and it is compiled, and if it is successfully compiled, ELF file will be generated. So ELF file is visible here under the binary. So this is the file that we are supposed to run on the FPGA. Okay. Next step here, after we have seen that the ELF file is automatically generated, so the code hello world is given over here. This program simply prints hello world at this line, and let us first program the FPGA. Go to Xilinx tools, program FPGA. You will see that first of all we will map the hardware. The first file is system.bit file, and the second file is system_bd.bmm file, right? And boot loop is written here. You have to select boot loop and just click on program FPGA. So whatever configuration memory was created .bit file, a combination of ELF file so if the drivers is successfully implemented, we will see this USB serial driver and uh, USB, Xilinx USB cable. These two drivers are required. Okay, so let's now close it. And once again, the errors was coming because of the cable was not connected. So once again, we'll program the program. The file, click on the binary and click on run as and go to run configurations. No, run configurations. So there are two possibilities of looking at the output. One is the console, getting the output serially from the kit on the console, or configuring a terminal. Both are possible. So I am saying direct my standard output to the console. Okay, so in this case I'll click console, but the COM port should be correct. Is it COM1 or COM14? We have to check it. Again, go to the devices manager and check which is the COM port on which this port is there. So it's COM14. Okay, because USB serial driver is on COM14. So we'll click on COM14 and click apply, close. Now we can run as run on hardware. So now my program is running, and I am only getting H output on the console. So we can see this output coming hello world on the console. This was coming from the kit serially, right? So the second method here is to go for the terminal configuration. I'll again click on thing which you want to do is to look for output on the terminal. Let's do it once more and change the run configurations and click uncheck the connect STDIO to console. Now click on terminal and look the settings of the COM14, and these are the baud rates. In certain cases the baud rate may also change, so you may look for higher baud rates depending upon your device. Right now it is 9600. Okay, and click on connect the terminal. Now once again launch the program. So you can see the output now coming on terminal. The same thing, and the terminal is prompting. That means it is connected to the kit and it is listening at the whatever is coming solid onto the device. Okay. So these are two ways in which we can configure. Now I will stop the terminal. We have seen the output. The next step is to check our hello world program. Oh sorry, our now we are going to create one more application. Xilinx project is to test our adder at the software level. So I'll go to the empty application now. Create an empty application. Click on next. Click on the board support package which we have implemented, which is standalone PSP0. Click on finish. In this case, an empty application folder will be created and there will be no source files. So our first task is to add the source files which are created in driver folder and copy them over in the src directory. So this can be done. Let's see, source, import, general, file system, next, browse to e directory, new one, na? New one, new one has so many directories. Nee, the project was new one, na? We have to import drivers. this side, this driver folder was created during our creation in XPS. Now we'll click on all these files and finish. Right? So we can see the header files here. These are the header files created for our IP. And if you look at the functions here, the functions are like my IP name, write to the register, its base address, the register offset, and the data. Similarly, there is a read function. So these are the functions which are provided for reading and writing to the IP. Okay, so this is a test. Add the H file. Similarly, C file is there, which has the header file in it, and finally the self test file, which has the functions to call. But as such, there is no main function here. So we can write a file which has the main function. I will create a new C project. File name, let's say header test one. Finish. Okay. So this file has been added, but it is not able to find add as file, right? So that is the problem it is making. So let us again once again change it and change the directory under the source, then it will compile. So we have created this ad.seed file, and we have copied this code which is putting input as 3, output as input as 5, and we are expecting an output of 8 on the prompt to come with the adder which we have created. The only thing we need to change here is the base address of our IP, right? The base address, we have to go to the XML file and find the base address. So let's see what are the base address here. Okay, so this has a main function, and let us now build it.